So good afternoon, everyone. Thanks for coming to the talk. My name's Everspaugh. I'm from the University of Wisconsin, and I'm going to talk today about the Pythia PRF Service. So this is joint work done with Sam Scott from University of London, who's out in the audience. Also Rahul Chaterjee, Juels, and Tom Ristenpart, now of Cornell Tech. We're using passwords every day. We use these things to authenticate to devices, and we use them to authenticate to online services. But the way we store these passwords is fundamentally broken, because these password databases get compromised, and when they get compromised, they're vulnerable to offline attack. So today I'm here to present a new approach, a complete architecture for protecting passwords, something built around a cryptographic PRF delivered as a service. It's a PRF we call Pythia. And this solution not only eliminates offline attacks, but it also enables us to detect online attacks, recover from compromises, rotate keys, also delete password databases that have been stolen. Okay, so let's start with a concrete example. If you go to LinkedIn's page today, this is what you see. To log on to LinkedIn, you provide them with an email address. You also type in a password. Of course, LinkedIn has to store this password some way. Okay, pop quiz. In 2012, how was LinkedIn storing passwords? These are the common techniques that people use. Thank goodness LinkedIn wasn't storing plain text passwords. But it turns out they were storing unsalted hashes of passwords. The reason we know this is because in 2012, LinkedIn was breached by attackers. They stole a large corpus of passwords, and they leaked these online. When they were leaked, security researchers had a field day. They ran offline dictionary attacks. They were able to recover most of the passwords in that body. So the attacks were so efficient here because we're using unsalted hashes. But I want to point out that even if LinkedIn had been using industry best practices, if they were using iterated hashes and salts, this only slows attacks down. This doesn't keep attacks from happening. This means that passwords can still be broken. Okay, I don't mean to pick on LinkedIn only. Password database breaches happen to a lot of people. Sophisticated tech companies, online media companies, software companies. Lots of people have this problem. The end effect is that password database breaches occur. We want to limit these breaches, of course, but since they're going to occur anyway, we need to have some scheme to make sure that passwords don't leak when databases are breached and this information is leaked. Okay, so let's look at a better approach. So early this year, in January at Real World Crypto, Facebook presented this. They call this their password onion. So real quickly, the way this works is when you log into Facebook, they take your password and they run it through this series. First, they hash it with MD5. Then they add a salt, HMAC it with SHA-1. Then they connect to a remote server, run it through an HMAC SHA-2 with a secret, send it back, run it through scrypt, run it through HMAC SHA-2 again. So you're probably thinking this looks a little complicated. You might be asking yourself, why does Facebook do it this way? Well, the reason here is historical. So once upon a time, Facebook had 1 billion hashes in MD5 sitting in a database. And they decided, rightly so, hey, MD5 is not going to work. We should switch to SHA-1, and we should add a salt. But you've got 1 billion passwords in a database. You don't want to tell everyone to reset their password. It's also unreasonable to expect everyone to log in on the same day, just so you can update your code and update your database. So what they did was take the existing database, add a hash, and a salt, and then rewrite the database. Of course, at some time later, they decided SHA-1 wasn't good enough. They switched to SHA-2, in this case on a remote server. Then later they decided they have to use scrypt. The scrypt output is too big, so then they have to add SHA-2. So unfortunately, what we're left with here is this code, which is like an archaeological record of Facebook's struggle with passwords. But I want to point out something else, something really interesting here. So there's this remote call here. And what Facebook's doing here is something that most people aren't doing. So somewhere in their password processing, they connect to a remote machine. They ask that machine to hash their password with a secret held only on that machine. And this is really nice. The reason this is really nice is it leads to a different kind of architecture. So at a really high level, user submits a password, web server does some processing, connects to a remote server who then does the hash. And the reason this is really nice is because this separates critical information between the web server and the crypto server. And this is nice because if an attacker breaks into one machine but not the other, he has insufficient information to run an offline attack. So this is a nice property, but this still has some limitations. So the first thing you'll notice is there's that secret on the crypto server. So as a security person, you're probably asking yourself, how do we rotate this secret? And the case in Facebook's example is there really is no way to do this. There's no good way to change that secret without simultaneously destroying your database, in this case, a database with 1 billion passwords. There's also another problem. The way they've set up this interface, each password guess looks unique. And so what happens is, it's going to be really difficult for the crypto server to distinguish between a high volume of legitimate requests from a web server, each with password submissions from different users, and an attacker who's running a dedicated attack. So if someone's stolen the password database and has access to the crypto server, he can submit guesses, and he may be able to hide in the normal traffic. Okay, so we want to fix these things. So for the rest of the talk, we're going to leave behind the state of the art. And I'm going to present our approach, our contribution to solving this problem. So we want to inherit some features of this architecture. We want to split information between the web server and the crypto server. And in our case, we're going to call this server the Pythia PRF Service. And we need some additional advantages. So first is we want to change the API. We want to expose enough information that the Pythia server can now detect the difference between a series of legitimate requests and a targeted attack against a single account. We also want to be able to rotate secrets. So this will help us with compromise recovery, and it's also going to enable us to do proactive key rotation. Finally, with compromise recovery, this will give us the ability to remotely erase password databases that have been stolen. And we want to make this easy for lots of companies to use, not just for Facebook. So what we really want is a multi-tenant service, some third-party service that can serve lots of clients. And yet, somehow, those clients can inherit the trust of the service and not have to just hand over a list of usernames and passwords. Okay, so what I want to do is walk at a really high level through a flow of how the Pythia PRF service works, and then we're going to dive into some details. Okay, so we'll start with enrolling a new user. So in our case, we have a web server. It's using the Pythia PRF service to protect passwords, and a new user is logging on. So the user supplies a username and password. The web server chooses a random number. We'll call that T, and this is going to be a user ID. He then takes the password, runs it through a blinding function, and I'll show that to you later. And we're going to call that result X. The web server connects to the Pythia server and issues a query. And the query comes with this information. A value W, this is going to be a unique identifier for the web server, the user ID T that we just generated, and this blinded password X. Pythia server is going to choose a key K, in this case a key assigned specifically to this web server. This gives us an instance of the PRF only for this server. And he's going to run the value, the user ID T and the blinded value X through some PRF, in this case a keyed PRF, F sub K. He then sends back the result. Web server applies an unblinding function, and when he's done, we get a protected password. We'll call that Z. Now the web server is going to store these values: user ID, or username, user ID T, and the protected password. Then when the user comes back to the site later, submits a new password PW prime, web server runs some variant of this protocol, gets a new value Z prime, compares to the value stored. When they match, he knows the password is the same. Okay, so this is how we do PRF queries. How do we do compromise recovery? So web server has this database, a bunch of these values, Z0, Z1, etc. Attacker breaks in and steals a copy. Well, the good news is he can't run an offline attack. But let's say the attacker has access to the Pythia server. He can now submit queries. But now the Pythia server requires each query to come with a web server ID and a user ID. This means the Pythia server can clearly see if there's too many requests on a single account. So the Pythia server can take some action. He can ban an IP, he can rate limit queries. Probably most importantly, though, he can send an alert to the web server that says, hey, I see anomalous activity. If this service isn't coming from you, then there must be a problem. Somebody must also have your password database. Okay, so now the web server admin knows there's a problem. He cleans up the web server. Maybe he fixes his SQL injection problem. But now he wants to update his passwords, away from the key K and onto a new key K prime. So the admin contacts the Pythia server, requests a new key. The server generates a new key K prime and sends to the web server a compact token. We'll call this delta. So this is a token that's going to allow the admin to update the encryptions from the old key K to a new key K prime. So the admin runs some update process, updates all the values Z to new values Z prime, and this whole thing can happen without user interaction. So the web server doesn't have to have the original password, doesn't have to involve the user at all. And in fact, the user password is still the same, but we've updated the encrypted passwords. And then, of course, when the web server is done, it contacts the Pythia server and says, hey, I'm done with key k, I want it erased. So the Pythia server erases key k, and now we've made this password database useless, because these passwords are encrypted under a key which the Pythia server no longer has. So this is a nice property, right? This allows us to cryptographically erase stolen passwords. Okay, so some of the cryptographers in the audience are probably already thinking about some of the features we're asking for and how these map onto existing primitives. So let's go through all the features we need. Okay, so we need a scheme that's deterministic. So given a password and the same key, we need to make sure it produces the same result every time. We also need the output to be pseudorandom, especially if we want to use the derived value as some kind of a key. We need some kind of partial message privacy. We want to require the requester to supply some information, but we want to hide the password from the Pythia server. And of course, if we want to do compromise recovery, we need some scheme that allows us to update keys and maintain the same values underneath. Okay, so pseudorandom functions, oblivious pseudorandom functions, these give us some combination. We have partially blind signatures, which give us some kind of partial message privacy. There's things like key updatable encryption and proxy re-encryption, which allow us to update keys. But if we look at the intersection of all of these things, and this was something we found particularly interesting, is that we couldn't find any existing primitive that actually gives us all of these features simultaneously. So what we had to do is introduce a new primitive. This is something we call a partially-oblivious PRF. At a very high level, essentially we're taking features from partially blind signatures and we're combining them with deterministic pseudorandom output that you'd get from an oblivious PRF. Of course, along with a new scheme, we need some new security definitions and then some new proof techniques for proving security. Okay, so real briefly, I'll go through our construction. So the construction we propose uses a bilinear pairing. For those who know, this is a function E. It maps inputs from two groups, G1 and G2, onto a third group, a target group, GT. And in particular, we need a function E that satisfies this identity. So given groups and given such a function, we can then define our PRF. So the blinding function is this. We take the password, we hash it onto the group, we raise it to the power of some R, which is some randomly chosen value. We submit our query to the PRF server. PRF server chooses a key. It then applies this PRF function. So what we do is we hash the user ID T, we run that value and the blinded value X through the function E, raise the whole thing to the power K, that's the secret held by the Pythia server. When the web server gets the result back, he applies the unblinding function in the natural way, which is to raise the whole thing to the power of the inverse. So if we write out what that means, this is the result we get. And what we see is that the blinding factor R and its inverse cancel out. And what we're left is a value computed over a hash of the user ID, hash of the password, all raised to the power K. And so we've seen similar uses of bilinear pairings before. Sakai, Ogishi, and Kasahara, they use this for their non-interactive key distribution system. Also Dan Bonnet and Waters, they use this for their left or right constrained PRFs. Those are slightly different contexts, and so here we have different notions of security. We have distinct security goals. Okay, so once we have a PRF function supplied, doing an update function is very straightforward. A compact token delta is then the key k prime divided by k. Update function is then taking an existing value z, raising it to the power of this update token. If we expand what that looks like, what we see is that the update token cancels out the existing key and gives us a new protected password covered under the new key. Okay, so that was really detailed. So let's pop back up to the big picture and let's see what all that buys us. So using a construction like this, what do we get? This gives us a scheme that allows the Pythia PRF service to learn enough information to distinguish online attacks from legitimate traffic, but at the same time, the Pythia service never learns the password. And also, the web server doesn't learn the secret key, but he can still get an update token, which allows him to update encryptions from an old key onto a new key. And our goal here is to build something that's relatively easy to deploy. So if the Pythia PRF service is being provided by a third party, what we want is that a web server that wants to enroll in Pythia just needs to download a library, update a few routines to include connecting to a Pythia server and then storing that data. What we want is there should be some relatively small change to the code base. And in particular, we want to have is no impact on the user experience, right? So the user still logs in using the normal username and password. The user doesn't have to do anything special to use a web server that's using Pythia. Okay, so we were inspired by the Facebook password onion. We designed a password onion of our own that uses Pythia, but ours is now a parallel password onion instead of the serial onion that Facebook uses. So in particular, we have a scheme that allows us to combine the strength of iterated hashing with the Pythia server. So the way this would work is you log into a web server, supply a password, and then in parallel, the web server kicks off some expensive hash function. It could be iterated hashing, or if you like, some other very hard function like bcrypt or scrypt. At the same time that's computing, the web server can issue this Pythia PRF query. It runs this protocol, gets some result Z, and what we want to do is combine these results. And so we take our Pythia result Z, raise it to the power of this iterated hash function A, and so now we have a result which combines iterated hashing and our Pythia query in a way that still preserves key updates. And this is really nice because if we tune our iterated hashing such that the Pythia PRF query is at least as fast as the iterated hashing, what we'll see is that there's no change in the performance profile. Logins take just as long to complete, and we get better security overall. And the reason this is nice is because in the extraordinary event that both the web server and the Pythia server are compromised, the whole scheme collapses down to this iterated hashing scheme, and so your security is no worse using Pythia than if you were just using an iterated hashing scheme. Okay, so we built one of these things. It's open source. We built it on open source components. The source code's on GitHub. You can find links on our webpage. We also have a test and development server at remotecrypto.io. Also on GitHub, there's a sample application. It issues queries against our test and development server. You're welcome to use it, play around with it, do whatever you like. So the service we built is fast and scalable. PRF queries are fast. Even though we're using bilinear pairings, computers are fast and we have modern implementations. So on a LAN, meaning both the Pythia server and the web server are in the same data center, queries are very fast. We can do those in 12 milliseconds. Over the internet, of course, they're going to be much slower, but still we can execute these queries in less than 100 milliseconds. Throughput is good. We can get over 1,300 connections per second on a single EC2 instance. To give you some sense of scale, this is within a factor of 2 of fetching a static web page over TLS running on that same machine. And storage is very reasonable. So storage for the Pythia server is now constant for a given web server, independent of how many users are using that web server, right? Pythia server only has to store a small amount of information in the key table, and the web server can have an arbitrary number of clients. So to give you some sense of scale, if the Pythia server has 100 million web servers with an arbitrary number of users for each web server, the Pythia server only needs to score less than 20 gigabytes of data. This is because the Pythia server just has this small key table. We keep a web server ID, which is compact, and we keep a key associated with that. Okay, so what I've been presenting today has been an example of using Pythia for enterprise password management. And this is probably the most compelling use case, but Pythia is really designed to work for any scheme that uses passwords. So in particular, in the paper, we described something called a Bitcoin brain wallet. And this is essentially a Bitcoin wallet where the private key is derived from your password. Of course, if you do this just by hashing, your public key is now on the blockchain, and so it's at risk for offline attack. So in the paper, we give a more secure scheme where you can use Pythia and your password then to derive your Bitcoin private key. And any scheme that uses passwords and allows internet activity would be fine. You can imagine using this for file encryption. We could use the key rotation then to delete data on devices if they've been lost or stolen. You could also use this for message-locked encryption. So what's the takeaway from all this? Password storage is broken. Password databases get compromised, and when they do, there's no way to eliminate offline attacks. But we can fix this. We can build an architecture around the Pythia PRF. We can eliminate offline attacks. We can actually detect online attacks. And when we detect those, we can take action. We can recover from compromises, we can rotate keys, we can delete password databases that have been stolen. And finally, we can democratize access. You don't have to be a big company with Facebook and a giant infrastructure team to build your own Pythia server. If we can get third-party providers to build and host these services, we can make this accessible to lots of different companies. Thanks for your time, and I'd love to hear your questions.
Alan Sherman from UMBC. How do the properties of your system compare with those of a similar system by Taplink, whose security is based on data obesity?
I'm not sure if I know this Taplink. Is this also a scheme for protecting passwords? Using these like very large arrays that they hash into?
The high-level objectives are very similar.
Yeah, so if it's the scheme I'm thinking of, this is a really clever scheme, right? So Taplink has this scheme where they essentially populate several terabytes of data, and they use this essentially as a giant random oracle. It's this nice, like, non-portable cryptography, right? You can't break in and steal the keys. So that's about all I know about Taplink. It also has this scheme, it also has this property where you can't break in, steal some compact key, and now you can decrypt passwords. I don't know, however, though, if it allows you to do key rotation or this kind of cryptographic erasure of stolen information.
Hi, I have a clarifying question. So, just to understand, the attacker in your diagram cannot force the server, your server, to actually change key.
Yeah, okay, so a very good point. So I breezed over some of these details. But yeah, so if the attacker can force a key change, he can run a denial of service.
Right.
He may also be able to upgrade to a key and then steal control of the thing. Yeah, so these services would require some kind of additional authentication, right? And what we need is some kind of authentication that's, let's see if I can find the diagram. Some kind of authentication that's not stored on the web server. Because obviously if you can break into a web server, if I steal the authentication credentials, the whole thing collapses. So what we want is some kind of out-of-band authentication. Right? So a simple way to do it is a web server registers, sets up an ID, also sets up some out-of-band channel, maybe just an email address. And then when you want to execute one of these very sophisticated requests, like a key update, you have to go through some longer form authentication, maybe send you a verification code, maybe you have to supply a password.
And do you have, my second question, the second question is, can you comment on scaling this up to a scenario where you have, 10 Pythia servers all geo-distributed?
Yeah, so the front-end stuff scales very nicely because you can process these requests in parallel, assuming you have a single key table. So the idea being you have a single database serving a bunch of web servers. So that works really well inside a single data center. And so I think with typical scaling techniques, you could easily scale this up in a given region.